Dear, so welcome back to a new video. So in today's video we are going to see about ideal solubility parameter. So let us discuss about ideal solubility parameter, what it is, why we have to learn this. Yeah, actually solubility, we know solute will get dissolved in our solvent in the particular in the uh, temperature and pressure, right? Specific temperature and pressure. So what is ideal solubility parameter? Ideal solubility parameter is nothing but a numerical value, okay, that will teach about the intermolecular forces between the solute and solvent. So here which we are going to see how the solute is interacting with our solvent, okay, in the particular solvent, how your solute is going to dissolve, so that we can learn by the ideal solubility parameter. Okay, so first we can see the solubility parameter is a numerical value that indicates the relative solvency behavior of a specific solvent. That's what this ideal solubility parameter is mean for our solvent. Okay, so it is derived from the cohesive energy density, where it is derived from the cohesive energy density. This cohesive energy density is nothing but the intermolecular force. It is required to break a 1 mole of our liquid molecule. Okay, so this solubility, ideal solubility parameter, we have two types. One is the scientist Hilbrand has discovered, that is what Hilbrand solubility parameter, and the second one is the scientist Hansen has derived, that is Hansen solubility parameter. Okay, so first we will see what is the Hilbrand solubility parameter. So the Hilbrand said how the intermolecular force is basically the cohesive energy density. The relationship between the cohesive energy density is given by our Hilbrand. So Hilbrand in the earlier stage he said that is only the hydrogen bond is responsible for our what solubility. Okay, so we are getting the solubility due to the hydrogen bond. Later on he said the solubility is based on the cohesive energy density. Okay, in the 1936 again he said that the cohesive energy density, that solubility parameter delta, which is equal to square root of cohesive energy by molar volume, that is what delta is equal to square root of molar cohesive energy divided by molar volume. So as per your Hilbrand solubility parameter, we have high delta as well as the low delta value. In this high delta value, the strong intermolecular forces involved. The strong intermolecular forces is like hydrogen bonding is involved. And in the second case, the low delta, in that low delta, like dispersion force is involved. Okay, so this is responsible. Strong force means the intermolecular forces required will be it will be strong. In the low means the intermolecular force will be weak, it will attract more. Okay, so this is what basically the Hilbrand said. In Hilbrand said the cohesive energy density is responsible for the solubility. Okay, and later on the Hansen what has done, we know the means intermolecular, the relationship between the intermolecular forces, right? So Hansen said to predict solubility by considering three types of intermolecular forces that we already hear what Hilbrand found, right? So this Hansen divided the Hilbrand total solubility parameter into three types. Okay, that's what the types of intermolecular forces we have: dispersion force, polar force, and hydrogen bonding force. Okay, these are the three component system. So the first one is the dispersion force. We will represent it by delta D. Okay, that is the weak force. Okay, this is temporary force between the non-polar molecules. And the next one is the polar force, that is delta P. Okay, so the delta P is the forces between the permanent dipoles, And the hydrogen bonding is the forces, like strong forces between the molecules with the hydrogen bonding groups. So this is delta D, delta P, delta H. So the total solubility parameter delta T is the combination of this factors. So we can write delta T. Okay, delta T is equal to square root of delta D square plus delta P square plus delta H square. Okay, this is what Hansen done. Okay, so Hansen what it done? He divided the total Hilbrand constant, total Hilbrand intermolecular forces into 3 component systems. That means 3 intermolecular forces involved, right? So that is what dispersion force, polar force, hydrogen bond. And he written total Hilbrand parameter. That is the total solubility parameter, delta T into 3. That is square root of delta D square plus delta P square plus delta H square. This is what the Hansen. In the case of your Hilbrand solubility parameter, the first case we had to remember is the cohesive energy. Delta is equal to E, that means molar cohesive energy by molar volume. This is the second finding of the Hilbrand, and the square root of molar cohesive energy by molar volume is the second finding of Hilbrand. The first finding is what? The strong force but high delta, which that means hydrogen bond is responsible for the solubility, is the first finding, second finding and third finding. Okay, in the Hilbrand case we had 3 findings, and in the case of Hansen solubility parameter, whatever the Hilbrand total constant, he divided into 3 component system based on the intermolecular forces. Then this force you had to remember. That's about the ideal solubility parameter, and we have to know where it is applicable, right? So the applications is, if we want to select the suitable solvent for the particular drug or solute, okay, it will help solvent selection. Then formulation design, when we are going to formulate a particular dosage form, so the ideal solubility parameter will help. Then it also helps to predict the solubility and compatibility. Okay, I hope you people understood my video. If you have any doubts, please comment on the comment section. So thank you for watching. Bye bye.